Today we're going to discuss continuity of a function. From back in Algebra 1 or Algebra 2, wherever you first hear the phrase continuity, you may think of it as a function is continuous if you never pick the pencil up off of the paper. Now that we have some language with limits, we can provide a slightly better definition. It is as follows. First, a function is continuous at a given point c if the limit as x tends to c of f of x exists. Now, if you may recall from the last couple of days, the limit as x tends to c of a function really has two underlying problems. It's the limit as x tends to c from the left and the limit of x tends to c from the right. And in particular, they both have to equal the same thing in order for the limit to exist. Secondly, the function value must exist at c. Sometimes people might write this as f of c exists. And then next, and the last and most important condition, is that the limit as x tends to c of the function is equal to the function value at that point. It turns out that this last statement is the most important. So if you remember one thing, statement 3 is it. Just to kind of draw something on the side here of what this means is the first condition says the limit must exist. That is to say, if you look at a function at some point c, the left-hand side and the right-hand side have to attain the same value. And in particular, we can see as we approach from the left and we approach from the right, we get whatever that value b is. The second is that the function value must exist. Well, would you agree that the function value could be up there somewhere? So we would say that the limit exists and the function value exists, but the problem is the last condition is not met because the function value here does not equal the limit value here. So the function is not continuous. So the last condition, of course, is that the function value actually kind of plugs the hole, if you will, and that determines that it's continuous. And that's sort of the point of this diagram. So we'll look at diagram 2 here, and we're asked to find the limit as x tends to 2. Well, again, it's approaching from the left and from the right, and if we were to put in an artificial value here, it doesn't really matter, let's say 3, we would say the limit is 3. In particular, though, let's say the function value is maybe at 4, so f of 2 equals 4. And the idea from our previous discussion is that no, it's not continuous, and the reasoning would be the function value does not equal the limit value. So you could write the function value at c does not equal the limit value. Or I think simply just writing the statement 3, which is to say the limit as x tends to 2 of f of x does not equal f of 2. And I would say this is the best and most complete statement. And then definitionally, we also can talk about continuity at an endpoint. Of course, endpoints have a little bit of a problem because if we're looking at some kind of interval, say from here to here, let's call the interval from A to B. At A, you really can't take a left side limit, right? A minus, A from the left doesn't exist. And B doesn't exist coming from the right, or B plus. So we can see that a function y equals f of x is continuous at the left endpoint if the right side limit exists. And we can see that a function is continuous at the right endpoint B if the left side, or b minus, interval exists. Basically what this is preventing is a situation like this. Imagine, again, an interval from a to b, where the function may be open on the endpoint and then filled in up higher. In this case, we see that the limit exists, but the function value is something else, so we would say that that is not continuous. Okay, a couple other important points. Continuity over an interval. Simply stated, function is continuous on the interval a to b, and we'll make it a closed interval from a to b, if and only if, the IFF, if and only if, it is continuous at every point in the interval. So I'm going to say at every point x in the interval from a to b. Okay, so at all points in the interval. By the way, notice that includes the endpoints. And if a function is continuous, we would say that a function is continuous if it is continuous on its domain. And maybe clearly we would say at every point on its domain. But take your pick on the language you like. Okay, now we have the question, is f of x equal to 1 over x continuous at x equals 0? Well, normally I would say evaluate this analytically, but we can do a pretty easy rough sketch here because this is one of those parent functions you know from Algebra 2. There's a vertical asymptote at x, x equals 0, horizontal asymptote at y equals 0. We know that the function will behave something like this. So visually, we can clearly see that the function is not continuous at x equals 0, and we can even do that from our baby language of Algebra 1, that we'd have to pick the pencil up to draw the left side and the right side, because we have to pass through that vertical asymptote. We can write this very simply as that the limit as x tends to 0 of f of x does not exist. By the way, the same reasoning applies for b. The answer is no. And even though we're only looking at the interval, say, from -1 to 1, the bad point, x equals 0, is still included. So the reasoning, again, is limit as x tends to 0 of f of x does not exist. Now, this last question is an interesting one. It says, is f of x equals 1 over x a continuous function? And after all the work we did in those last two parts, I think our obvious answer is no. Turns out that's incorrect. So what we have to consider for this problem, and it's maybe badly worded, I don't know. It says f of x is equal to 1 over x, a continuous function. The answer is yes, on its domain. Okay. The reason for that is this particular function is defined on the interval from -infinity to 0, union 0 to infinity. So that bad point, x equals 0, is not included. So the answer is yes, on its domain. However, you would also be correct to say no over the real line. So be careful about how you answer the question. In general, I think if we ask if it's a continuous function, we're talking about specifically on its domain. And by the way, not all functions are necessarily continuous on its domain. And I think we'll see some of that in our next example. Okay, so looking at the example, we're trying to find the limit as x tends to 0 of f of x. Now, this question really only allows us to do a one-sided limit because we only have the right side of the graph here. So as we approach 0, only from the right-hand side, we get 1. Now we take the limit as x tends to 1. Well, notice the left side tends to 0, but the right side tends to 1. That means the limit can't exist because the left and right sides don't agree. Now we're asking for the limit as x tends to 2. So from the left, we seem to approach 1, and from the right, we seem to approach 1. So the answer is 1. Limit as x tends to 3. Again, this seems to approach 2 from both sides, so that's the limit. And for 4, it's still a one-sided limit, so we're taking the left side, and we find that we just get 1. All right, f of 2. This means the function value at 2. Even though the limit appears to be at 1, the actual function value is here at 2. So f of 2 is 2. And similarly, when I look at f of 1, that's the function value evaluated at 1. That's where the solid dot is, and it evaluates to 1. It says, is this thing continuous on the domain from 0 to infinity? I think the answer is pretty obviously no, but we should provide a few pieces of justification. One place for justification is that the limit as x tends to 1 of whatever this thing is doesn't exist because the left and right side limits don't agree. Another reason that's a problem, it happens at x equals 2. At x equals 2, the limit exists, right? We found that, no big deal. The function value exists, no big deal, but check it out, they're not equal. So also, the limit as x tends to 2 of the function does not equal f of 2. So that's also a problem. And that's the third condition, and if all else fails, the third condition is the one you can use to remember everything. It says, for what values are there points of discontinuity? Well, I think we identified those in question 8. At x equals 1, there's a point of discontinuity. We actually call that thing a jump discontinuity. Maybe we'll address that in the future, I don't know. It's a jump discontinuity because the graph jumps from one value to another. The justification is that the limit as x tends to 1 of the function doesn't exist. And another place is x equals 2. In this case, we actually call that a point or removable discontinuity. And that is to say, the problem is that the limit as x tends to 2 of the function does not equal f of 2. So not continuous there. I guess we'll... Oh, number 10. It says, is this a continuous function? I think we've already addressed this. The answer is no, not continuous at x equals 1 or 2. So that's it. With that, start your homeworks.